Welcome, and today we are talking about this interesting concept of Poisson distribution through this app, Explorer app. Here we will be talking basically two tabs, Explore and Engage tab, where we have probability mass function, PMF of Poisson distribution, and then we will also be talking about explanation tab here. And here we have this formula for computing the PMF of Poisson distribution. So before getting into this formula, we have to understand couple of things about Poisson distribution. First main property is that it deals with discrete random variables. And this means that it describes the number of events occurring within a fixed interval of time or space. So this is first thing. And second thing is that it is something that relates to number of events, of course, right? And it is used to model the number of events that occur in a fixed interval, right? For example, number of emails that we receive in 1 hour, number of customers that arrive in the store or step into the store in 1 hour or go through drive-through, or number of calls received in call center in maybe 1 hour, right? So these are events, right? And we are studying those events. And this rate of occurrence is called lambda here. So the only parameter that you need in this distribution, Poisson distribution, is average number of events, and this is lambda. Of course, this is an average. So this is the mean of the distribution. And another feature that we have to keep in mind is that events are independent, right? Sometimes we also call that Poisson process is memoryless, which means that event occurring in the future is independent of the events that have occurred in past. So kind of the events are independent or memoryless, we also call it. Small probability, large trials. This is very interesting. Poisson distribution is often used in scenarios where probability of single event is small, but the number of trials is large. So this is another property, right? So with these pieces of information on hand, let us talk about this amazing formula of Poisson distribution, and it helps us calculate the PMF, the probability mass function, and it reads as P of x equals k equals lambda to the power of k times e to the power of negative lambda divided by k factorial. So let us now break down this formula and go through this by step. So this first part, P of x equals k equals represent the probability of exactly k events occurring in this interval of time or space, right? Exactly k events. And lambda, that is average number of events in the interval, right? This is also sometimes known as rate of occurrence. And E, of course, we understand is natural logarithm, and its approximate value is 2.71828. And K is the number of events, which can be any non-negative integer, right? So k factorial, of course, is the factorial of k, which means multiplying all the whole numbers from 1 to k. So this is how we understand the formula. And if we take this example, for example, we are talking definitely of application of Poisson distribution in quantitative finance or in any situation which is a corporate finance situation. And maybe let us take this example of insurance policy holders, right? Suppose an insurance policy holder files on an average 3 claims per year. Now we can use Poisson distribution to estimate the probability that this policyholder will be filing exactly 4 claims next year, right? So in this case, what will be happening? In this case, our lambda would be 3 and our k would be 4. So when we plug in these values into our formula, 3 to the power of k times e to the power of -3 divided by 4 factorial. So this calculation, if we go through step by step, then we get the probability, right? Probability of x equal to 4 is 81 times of 0.0498 divided by 24, which is approximately 0.168, or we can just say 0.168. So in simple words, the probability that policyholder filing exactly 4 claims in the next year would be 16.8%. So this is how we understand it. So this distribution is very interesting distribution. And here we have done these calculations. And here when lambda is 3, right? And number of events is 5, then the probability of exactly 5 events is 0.1008. Similarly, when lambda is 3 and number of events are 4, then PMF, the probability of exactly 4 events is 0.168, which we just did in these calculations here. So this is also shown through the calculations here. Right? So this Poisson distribution is amazingly well used in our corporate finance and quantitative finance situation, right? We can use it in case of defaults in the loans that might be happening, right? For example, if a bank has a large number of small loans and historically sees that there are 3 defaults per month, then Poisson distribution can be used to calculate the probability of having 2 defaults, 3 defaults, 4 defaults next month, right? So this way it can be used in many quantitative finance situations. Similarly, every business receives buy and sell orders, right? Suppose 10 buy orders means purchase orders arrive per hour for a specific stock, maybe with a stockbroker, right? Then Poisson distribution can help to predict that what is the probability of receiving, say, 8 purchase orders in next 1 hour. So this way, right? So nowadays we know that there is a lot of high frequency trading happening, right? And suppose in a high frequency trading software, 500 transactions per second can be processed, then Poisson distribution can be used to predict what is the probability of exactly 550 transactions would happen in next one particular second, right? So this way, Poisson distribution has many applications in corporate finance and quantitative finance situations, right? And it is very important and good to have a hold of that. This is how we understand it through our web app. And here 0.168 is represented here through this fifth bar in the plot, where there are 4 exact events happening and this probability is 0.16. So similarly, number of events on x-axis, we have taken it to up to 10, but theoretically this can go up to infinity. So this is very important thing, that x-axis on Poisson distribution is actually limitless, in the sense that values can go up to infinity. This is actually one of the difference of Poisson distribution from binomial distribution as well, right? Although we have plotted up to 10 only. So this way, although the probability then will become infinitely small, right? Thanks for joining.